In this problem, instead of being asked to use the information to calculate the confidence interval, what it's done for us is it's actually given us the confidence interval, and it's asking us to find sample size. As you've read in the textbook, sample size has a big impact on the confidence interval, whether you're working with means or in this section, you're working with proportions. Okay, so let's read this and get the context of it and then figure out how we're going to solve it. It says this: obesity is defined as a body mass index of 30 kilograms per meter squared or more. A 99, I'm going to circle the important information, % confidence interval for the percentage of U.S. men aged 18 to 19 who were obese was found to be, right, so the confidence interval is 18.8% up to 21.5%. It then asks this: what was the sample size? Round the intermediate calculations to 4 decimal places and round up your final answer to the next whole number. So let's see what this means, right? We're used to having information and finding, like we said, the confidence interval. But instead, we have the confidence interval, and we're going to work backwards. We're going to start by remembering that our margin of error is equal to our z sub alpha over 2 times the square root of PQ all over n. The reason I write this down is that instead of using my margin of error right here and adding and subtracting from the sample proportion, the sample average to get these values, we're going to end up going backwards. So here's what I'm going to do. I'm first going to take a look at my 18.8 and my 21.5. And I'm actually going to find the difference between those two. So to find the difference, I'm going to actually write them the other way. 21.4 minus 18.8. And when I do that, I believe I get a 1.6. So the distance or the difference between the two ends of my confidence interval is 1.6. Let me verify that calculator really quick. 21.4 minus 18.8, like I thought, missed a whole digit there. It's actually 2.6. Okay, so 2.6. Okay, now, if the distance from the lower end here to the upper end of my confidence interval is 2.6, what do I know my margin of error is? My margin of error is actually half of that. It's 1.3. Because in order to find a confidence interval, you take that middle value and you add and subtract 1.3 to get the 18.8 and the 21.4. Okay, so I know my margin of error is 1.3. So I'm going to go back to this equation right here, and I know that I calculate my margin of error by knowing my z-score, my p, my q, and my n. Here's the thing though. I know what my z-score is here because I know I'm working with a 99% confidence interval. Now I don't know my population data for p and q, but I think I can actually figure out an estimate using the sample proportion. Okay, when you work backwards, you actually have to use the p hat and q hat. Based on this, what is halfway between 18.8 and 21.4? Well, halfway between 18.8 and 21.4 is 20.1. So P hat is equal to 20.1, which means Q hat, and that's percentage, which means Q hat is going to be equal to, let's see, that makes that a 79.9%. Okay, good. Let me get rid of this real quick so that I can write these as decimals. This as a decimal is 0.201. This as a decimal is 0.799. That'll be important because in our equation over here, we know that we need this in decimal form. Now, in your textbooks, it actually does something pretty nice. It says we know that there's going to be scenarios in which we want to know sample size based off of the result. So it takes and solves this equation for n. It solves it and says that n is equal to p hat q hat times excuse me, z sub alpha over 2 all over e squared. So all it's done here is it's divided both sides by z sub alpha over 2, squared both sides, and then the manipulation of pq over n to solve that for n gives you what we have right here. So, interestingly enough, everything that I've talked about up to this point actually leads us to this formula right here. Do I know p hat? Yeah, it's 0.201. Do I know q hat? It's 0.799. Do I know z sub alpha over 2? Well, that comes from being 99% confident. If you look back from previous sections that deal with z-scores, we know that a 99% confidence level gives us a z-score of 2.58. And then my margin of error, we said, was our 1.3. So I'm going to say that my value for n, my sample size, is equal to 0.201 times 0.799 times my 2.58 all over 1.3 squared. So I take a moment, get my calculator out. I'm going to do actually go back, 0.201 times 0.799 times my 2.58 divided by 1.3 quantity, and that's going to get squared. Now, if I do this, I've made a mistake on purpose. Okay, if I do this, I end up with a value of 0.6325. That is definitely not my sample size. This would say that I took a sample of 0.6 people. Okay, what is the mistake that I made here? Okay, this is a very common mistake, so I wanted you to see it done, and then we'll make the adjustment. The mistake is the form our margin of error is in. The form our margin of error is in is actually in percentage form. But just like we had to convert P and Q from percentages into decimals, I've got to take my margin of error from percentage into decimal. My margin of error from percentage of 1.3 into decimal is 0.013. So if I go back and I adjust my calculation to 0.013, it ends up giving me quite a different value. Same numbers, interestingly enough, but everything shifted. It ends up giving me a value of 6325.51. So it says, in order to be 99% confident of the true proportion of 18 to 29-year-old men who are obese, in order for that confidence interval to be from 18.8% to 21.4%, I know I have to have a sample size of 6,325.51 men. Now, we know we don't want decimals for sample size, so we always round up. It does not matter what the decimal is, whether the decimal is a 0.1, 0.2, 0.3, does not matter, 0.5, 0.7, 0.9, we always round up. And so my final answer is going to be 6,326. So if I want to achieve this result right here at the 99% confidence level, I know I need a sample size of 6,326 men.